Good. So we will continue from last class. So last class we looked at the well growth curves, right? So what is a well growth curve? So we plot a well nugget diameter as a function of current or time, okay? And then we can identify the Imax and then the critical diameter required for the engineering application. So we looked at IT as a function of well nugget diameter, okay? So generally the curve goes like this, a typical application. So we can identify the maximum current for a given time. So that is Imax. So Imax determines the expulsion condition for expulsion or splashing, okay? And then guidelines for automotive industries generally says that the well nugget diameter should be 4 times the square root of thickness, okay? That is the ideal well nugget diameter. So I mean you can expect. So you can identify from the well growth curves. So what is the critical current and then time needed to achieve the required well nugget diameter, right? Okay. So why is it important? Because the mass effect M. So the mass effect determines the heat energy needed to form a given well nugget diameter, isn't it? So the M is related to Cp, and then again, so M is related to the mass and the density and volume, right? So we can identify by identifying the Q, then we can also calculate INT. So that's the relationship. And we also looked at some geometrical the advantages, disadvantages of the resistance spot welding. So what is the minimum distance needed between two wells? So the S is the distance between two wells in an overlap joint. So generally when you have an overlap distance of L, okay. Okay, so if this is L, the overlap distance, so what is the distance at which you will have to place the well, right? So generally that is an L by 2, okay. So you will have to place the wells, half a distance between the overlap, total overlap distance. Distance between two wells, the S, that is also very critical, because so if you keep it too close, then you may also have shunting, okay. So shunting we will see in this class, what is shunting and then why it is problematic and why it is important to analyze the minimum distance so that you do not have a shunting effect, okay. So the distance between two wells also critical in terms of structural stability, right. So when you are when the design is considered for an automotive industry, so they also look at detailed structural analysis, okay, to see how the member is behaving under a load, static and dynamic load, and they do a stress analysis to identify where exactly they can place the weld, okay, by considering the shunting effect, okay. So the S and L we can get it for varying thicknesses, varying materials, and then I showed you a table which you can be referred for a common engineering alloys. So for a detailed case, for example, if you want to identify what is the L and S, you will have to do a complete structural analysis using an FEM. So generally it is done for automotive component. When they conceive the design, they do an elaborate structural analysis, okay. So they think about the designs. So when they also conceive the design, and they keep in mind that which welding process they are going to use, because in a resistance spot welding the disadvantage is the accessibility. Both electrodes should be reaching to the same spot, okay. Suppose if you have a complicated geometry, some sort of curvy geometry, then you can't reach the spot from top and bottom, isn't it? So the design consideration involves what welding process they are going to use it for the component. For a spot welding you need to always have an access in top and bottom, isn't it? Otherwise you can't make a spot weld. So the design analysis when they are conceiving for a component fabrication in automotive industry, so they consider all the aspects, not only the stress analysis, they also look at the accessibility for the electrodes to reach the same spot, right? It's clear. So this is what we looked at in last class. So we look at in this class some of the testing methods they use for spot welding, resistance spot welding, right? And then we will see some of the definitions of some parameters which is used to define the quality of the weld, the mechanical property of the weld, right? So and then we will move on to the some of the problems you may face in resistance spot welding, right? It's clear. So any questions so far in last class? Okay, then good. So we will move on. So the common testing methods we follow to qualify resistance spot weld is these three. So, if you look at the sample geometry is what I have placed here. So, this is a simple tension, right. So, this is a simple tension test. So, what do we do in this case? So, there is a spot weld, right. So, we make a spot weld of two plates in overlap configuration, the same configuration I have been talking about. Okay. So, this is the most common configuration we use for spot weld and overlap, right. And then so upon making a samples, we fix that in a tensile testing machine, okay, and then pull it in tension and identify load required to break this bond apart. Okay. And in this process we identify what is the maximum strength this interface the weld can withstand. Okay. So, in this case, so generally it is a shear strength, because even if you are pulling it up, so the interface will undergo a shear loading. Okay. So, we identify shear strength, okay, generally as a function of weld nugget diameter. Okay. Weld diameter, and this follow the similar trend as a current arc. So, shear strength can also be replaced, okay, with the elongation as well. Okay. So, generally we plot the shear strength as function of weld diameter and identify the what weld diameter obviously gives the best strength, right. And apart from strength, and we also look at some other important parameter in spot weld, because when you are deforming such a member, you are applying load in almost in all the parts of this component. For example, this is your sample. When you are applying a load, the load is applied in all the places, isn't it, right. So, when you are measuring ductility, you are not measuring ductility of the weld, you are measuring ductility of the entire sample, isn't it, right. So, in order to identify what is the actual the property of the weld, apart from the strength and the ductility, we also look at the plug ratio. Okay. Right. So, what is the plug ratio? So, plug ratio we measure after the failure whether the weld nugget is intact or not. Okay. Suppose if you look at two samples after failure in this case, okay, sample A and then sample B, right. So, what I show you here is the samples after subjecting them into tensile testing. Okay. It is not pure tensile, but the cross tension test, but anyway. So, not to explain the plug ratio, you can refer this figure. So, what you see over here is this is the cross section and this is the top view of the weld, right. And if you look at the cross section, in this case the top image, this image. So, you see that, so this is the weld nugget after failure. You see the failure has happened from the interface, and then once the crack reached the middle of the weld nugget, and then it deviated and then failed vertically, isn't it. So, if you look at the plug, so this is the fusion boundary of the weld, isn't it, pre fusion boundary of the weld. So, when you are testing it up, so crack nucleated and then the interface opened up, and then ultimately the crack deflected and then it cracked like that, right. So, in this case some amount of weld is still intact, isn't it, some fraction of weld is intact, right, and we call that as a plug, right. So, we measure the plug size, right. So, the plug size can be measured. The plug size after testing over the initial weld nugget diameter, okay, and that is known as plug ratio. So, plug ratio we measure by measuring the plug size after welding. So, it is like you have a button, okay, you pull it apart. If button is intact, what is the plug size? It is 1, because the plug size is the same as the weld nugget diameter. Say the image over here in this case. So, in this case the failure has happened, from the fusion boundary it is deflected. You see that plug is more or less intact, is not it? Yes or no? So, the entire plug is opened up. You see the bottom plate, it is a hole. The entire weld actually it is intact, sticking to the one of the plates, is right. So, plug ratio here is the weld anchor diameter divided by the plug size divided by weld anchor diameter. That means that in this case 1. Okay. So, obviously during this test, if the plug is intact, what does it mean? The weld did not fail. The failure has happened elsewhere in the base material or heat affected zone. Okay. So, apart from the strength, it is also important to understand the plug ratio. Okay. So, when you are measuring the mechanical properties of the resistant spot weld, it is important to understand not only the strength of the weld, because strength of the weld, if you look at in this test, it is a function of even base material, is not it? So, base material is also contributing to the actual the strength. So, that is not a clear indication about the weld property. So, in order to identify quantify the weld properties clearly, so we also measure the strength required to break the joint, but this break can also happen in elsewhere, is not it, in the base material. So, but then that is not real identification of weld metal property. Okay. So, we identify the strength required to break anywhere plus the plug size, right. So, both combined would give us the mechanical properties. Okay. If a plug ratio is 0, what does it mean? Yeah. So, that means that the interface has completely failed. Okay. That means that you have a situation what you had before welding, isn't it? Complete interface failure. So, if both the plates comes apart after testing, what does it mean? That means that complete interface failure. Okay. If plug ratio is 0 means your weld is completely failed at the interface. So, you will have a complete interface failure. So, you will just take apart at the interface, isn't it? So, that means that you have an interface failure. Is clear? So, apart from the strength, the guidelines would also specify, so what is the minimum plug ratio you should have in order to qualify the weld. So, generally the weld qualification dictates that at least 80% plug ratio you should have, or 0.8. That means that the weld is not that brittle, the interface is not really segregated, it has a brittleness at the weld center line. So, if weld center line is completely embrittled, what happens when you are applying load? It will open, isn't it? Complete interface failure will happen, right? It's clear. So, we will have to identify the strength plus the failure mechanism in order to quantify the weld metal properties of the resistant spot weld, right. So, we do it in generally the 3 ways. So, one is a simple tension test. Okay. There are some problems because the load applied, it is not applied directly onto the weld. So, people have devised some other methodology. For example, in this case it is known as the cross tension test. So, in this case we make sure that the majority of the load you are applying, it is applied to the weld. Okay. So, you make cross samples, there are some standards you can there are controlled. So, you make a weld in the such and setup and then you apply a tensile load. For example, you pull the top in tension and similarly bottom in tension. Okay. So, in that case you also make sure that the load is concentrated majority at the weld, and you identify the strength required to pull this interface apart, isn't it? And then you also can calculate, because this will be slightly more accurate than this in order to quantify the weld, because whatever load you apply, because from the load only you are going to measure the strength. So, you can identify the strength of the weld. Okay. Is clear? So, plus the strength you also identify the plug ratio, right. It is clear. So, if both are matching, then the weld can be qualified. It is clear. So, the cross tension test is very commonly used in industry to test the mechanical property of the weld. And apart from cross section test, you can also do a tensile shear, L tensile shear. And this is simple to do, okay, because in this case you will have to make such a geometry sample and machine it, and then you will have to do, and this is very simple. So, you bend it, you make an L flange, okay, and then attach, make a spot weld at the middle of this L, isn't it, and then you pull in a tensile testing machine, pull it apart, and then identify the load required to break the in either interface or elsewhere. Okay, so the failure happens somewhere over here. Okay, that is best, isn't it? So, the weld is better than the best material, then the welders will be happy, right. So, if a failure happens at the interface, obviously the weld is brittle and it is not acceptable. So, the same way in this test also we will identify the strength required to cause a failure and identify the plug size after the failure. If a plug size is same as the weld nugget diameter, that means that plug ratio is 1, that is the ideal case you can achieve, isn't it, because the failure did not happen at the weld, the failure happened elsewhere. Yes, it is clear. So, these three are the common testing methodologies are used for quantifying the mechanical properties of the welds. So, the simple tension, the cross section test, or tensile shear in tension, right, it is clear. Okay. So, then we plot graphs like this. Again, if you change the thickness, obviously the weld nugget size can also change for a given current. So, in order to quantify the mechanical properties, we will have to measure it varying thicknesses. So, in this graph I plotted 3 thicknesses, 2.54 and 1.91 and 1.21, and then weld nugget diameter. Okay. So, obviously when the weld nugget size changes, the tensile shear force also changes, because if you are making in a larger weld diameter, so obviously you need to give more load to failure, isn't it? It's obvious. But if you are keep on increasing diameter, then after critical diameter you may not change. Of course, you will also have an I max, isn't it, and then you will have a failure by the splashing. Then the properties, I mean, you can't form a weld nugget. So, ideally, so that is why, so for example, in this case 2.54 mm, and you have one diameter that gives the maximum strength, right. So, after that you may also have severe cavity formation or indentation formation because of the more amount of liquid is there, and you may also have a surface depression. So, if you look at it in the weld case, okay, so you may also have a depression. So, because material becomes really softened if you have a large amount of liquid. So, there is a critical diameter upon which you may not really increase the strength. So, that is why generally that diameter is 4 by square root of thickness. Yes, it is clear. So, we identify from these curves plus the weld growth curve. So, weld growth curve will give us, so what current and time we may get the required diameter, right, and then we measure the strength as a function of weld nugget diameter, and then we identify, so what is the precise current and time we may have to use to identify the maximum strength containing weld, right, and then simultaneously we will also measure the plug ratio. So, you may also have a very good strength at that point. If the plug ratio is lower here than here, so then we may still consider this, isn't it. So, we can have a compensation for loss in strength with the better mechanical properties with the very high plug ratio, right, it is clear, yes or no, good. So, these kind of curves the measurements are carried out for each thickness for a given composition, because if you change the thickness, so obviously the mass effect would influence the weld nugget diameter, right, that will influence the current and time. So, that is how we generate the properties. So, we identify weld nugget diameter, the ideal weld nugget diameter which gives the maximum strength and acceptable plug ratio, right, it is clear, yes or no. So, this is how we qualify the spot weld. right? Good. So, this I already explained. So, how do you measure the plug ratio? So, plug ratio is measured, right. So, by measuring the plug size after the failure, is not it, and then taking a ratio between the weld nugget diameter over the plug ratio, the plug size after welding, we measure the plug ratio, right. It is clear. And then we can plot plug ratio as a function of weld nugget diameter or even current, okay. So, current or time or weld nugget diameter, and then identify if our plug ratio is always 100%. So, times 100, is not it, or 1 according to this equation. So, then that means that it is the best condition you can explain, and then you can identify which diameter gives the maximum strength, period, and then identify what current and time you will have to use to achieve that weld nugget diameter, and that you can identify from the weld growth curves. Weld growth curves are plotted as a function of current, time, as a function of weld nugget diameter. Yes, it is clear. So, this is how we measure the mechanical properties of a resistance spot weld. So, plug ratio is important. So, it is plug size after failure divided by the weld nugget diameter. So, if the interface failure, so how did the interface failure look? For example, in this case, if there is a complete interface failure, then you will have failure here, and this would have been gone, isn't it, the cross section. That means that the interface has become the same as it was before, and this could happen when you have a very brittle alloying elements segregating at the weld center line, okay. For example, say case like this. So, you have an material strength, the base material strength as a plotted function of strength, and if you have a high strength material, obviously to increase the strength you add a lot of alloying elements, is not it, carbon is increased, is not it, you also add silicon or aluminum or phosphorus. So, the material becomes very brittle. So, obviously when you add a more amount of carbon segregates to the solidifying liquid, and then weld center line becomes enriched in alloying elements like in carbon, then you may end up having an interface failure, is not it. So, interface failure means there is no plug at all. You see this in this case, the complete interface failure, whereas material with low strength you do not have much amount of alloying elements, as for example iron with 0.01% carbon, pure iron. So, the segregation is not that severe compared to the high strength alloys, which has a lot of alloying elements, phosphorus and carbon, and you see this plug is intact, is not it. So, this is a full plug failure where the plug ratio is 1, right, and if you increase the strength, so obviously the plug ratio decreases, you see that it becomes a partial plug, and then you have a full interface failure, right. It is clear. And why is it changing? Because in a conventional steels, and if you want to increase the strength of the steel, obviously you will have to add alloying elements, is not it. So, alloying elements can segregate and then make the weld center line brittle, and then if you are pulling it obviously. So, I already showed you, right, the notch effect, is not it. So, if you have segregation at the weld center line, because that is the region which solidifies at the end, if a crack propagates and then completes, then you will have a interface failure, right. It is clear. So, for ideal case, if you want to have a plug ratio is 1, so you will have to have a failure somewhere over here, is not it. So, the cracks would propagate and then fail somewhere here, that means that you have a plug intact, something like this. So, in this case the failure has happened far away from the fusion boundary, is not it. So, that is why you have a plug intact, a full plug, and then you can also identify the strength from the test. It is clear. How is it working? How do you qualify?